Okay. So yeah, so basically all the recording that will be put on the YouTube channel, and you can later also access it. I mean, like it will take some time before like it will be put there. So I will talk about basics of quantum error correction. I mean, there are 50 odd slides, but I mean, there is no intention to cover all of them. And like let's see whatever we can cover in next 1 hour 15 minutes, something. But let's say anyway, if you want to, like look at this, like, the details of, like, what are the different things that I will talk about and what I will not be able to talk about, all that, like, I mean, is there, like, I mean, I gave in 2023, I gave a tutorial series where, like, there are these things like classical error correction, basics of quantum error correction, stabilizer formalism, Tory code, introduction to topology, like basic things like homology, cohomology, topological quantum codes, subsystem codes, like decoder, fault tolerance, like all of this, like, it's recorded and the videos are there. So you can basically scan the QR code and get access. Anyway, like this, the slide will be later posted in the Discord channel. So if you are on Discord, you can, like you can access it. If you are not there, you can join the Discord channel and access them there. Okay. So let's start from the classical 3-bit repetition code. And I mean, before talking about quantum error correction, one should talk about classical error correction. And actually, it has a rich history. Like, I mean, uh, yeah, I mean, it's a very well developed subject, and lots of interesting work is still going on. I mean, and I mean, I really don't plan to cover, like, I mean, yeah, like, even a very small fraction of classical error correction. But I will talk about, the classical error correction, which is, like relevant for what we are going to talk today. So let's talk about, the classical 3-bit repetition code. So repetition, like, is one approach through which you can basically, like use redundancy to protect against error. So let's say you have some information, let's say you have some message, let's say, which is, written like a bit 001. What you can do is that you can repeat the message. So you can repeat your 0 3 times, you can repeat the second 0 3 times and repeat the 1 3 times. So it will become something like this, maybe 0 0 0 0 0 0 1 1 1. And in this way, by repeating, you have, you have taken a, like single bit message like here and converted into a, like a block of size 3, then block of size 3, block of size 3. So what happens that you take, like the code words are basically nothing but a repetition of the original bit. So the 0 logical is 0 0 0, 1 logical is 1 1 1. So that's how, like, I mean, we define this is the code words. Now, what can happen, like, let's say when you are sending it, like, or let's say you are storing the information, the bits can flip. So you can have the bit flip error. So 0 can become 1, 1 can become 0, and like this is a problem. So let's say you have some 0 logical, which is 0 0 0. If let's and the 1 logical, which is 1 1 1. Now, if let's say if the first bit flips, then the message will be 1 0 0 because the first bit has flipped. If the second bit flips, then the message will be 0 1 0. If let's say if the third bit flips, then it becomes 0 0 1. I mean, yeah, so that's the, the message after a single bit flip. Similarly, the 1 logical, let's say if this one flips, then it becomes 0 1 1. If this one flips, it becomes 1 0 1. And if this one flips, it becomes 1 1 0. So that's how, like after the bit flip, the code words become, Now, how do we know that, like some error has occurred? So the procedure to find out that some error has occurred is called like error detection. And if the bits in the string are not all identical, then that basically means that, like some error has occurred. Yeah. Okay. So for example, here the bits are not all identical. So you can just look at the bits and you can see that, like one of them has flipped. So, like it's Yeah, that tells you that, like some error has occurred. So that's how you find the error detection. For error correction, you will reset all bits to majority value. So you have, let's say, 0, 1, 0, you set it to all 0. You have 1, 0, 1, you set it to all 1. So because 1 is the majority, right? So that's how you do the error correction. Yeah. But assume, like, I mean, let's think a scenario where, let's say, you start with a 0, 0, 0, and like first two bits flip, it becomes 1, 1, 0. You notice that when you set it to majority value, you will be able to set it to 1, 1, 1, which is not what the original message was. So basically, in this case, like this majority, this reset to majority value is not working. Like, so there are limitations that you are already seeing. Also, for example, so in this case, you are able to detect error because, like, not all, like, bits in the bit string are identical. So you are able to do error detection, but you are not able to do error correction. What if, like, let's say, is from your 0, 0, 0, all three bits flip, so it becomes 1, 1, 1. In this case, you will not be able to, like, I mean, because all the bit strings, like all the bit in the bit strings are identical, you will not be able to even detect error. So like, so here, like, even error detection doesn't work. So the object, like, I mean, that captures whether you, like, what is the total number of uh, bit flips that can happen. You can still do error detection or error correction is captured by this object called code distance. So code distance is the smallest number of bit flips required to transform any two code words into one another. So here you have, like, the two code words that you have is like 0, 0, 0 and 1, 1, 1, and the smallest number of bit flip that you require to convert one to another is 3. So here that, like, that's called the distance. Now you can see that higher the distance, higher you will have, like, protection against the noise. So let's say if you have n bit repetition code, then in that case, like, this value will be equal to n. That's nice. After this, yeah, so you can capture the code distance using something called Hamming distance. So let's say you have two bit strings, like, you have bit string A and bit string B. The Hamming distance is the minimum number of bit flips to transform bit string A to bit string B. So for example, let's say the bit string A is 0, 0, 1, 0 and bit string B is 1, 1, 1, 0. In this case, if you, like, let's say if you flip just two bit strings here, like just two of them, basically you can go from this bit string to this bit string, yeah, just via two bit flips. So in this case, like, this Hamming distance between A and B, let's call this one B, is basically, like 2. So that the minimum number of bit flips to transform bit string A to bit string B. Now, if you see, the distance was defined as smallest number of bit flips required to transform any two code words into one another. And using this notion of Hamming distance, you can basically say it's the minimum Hamming distance between, like, any two code words. Like, that's how you can define, in the classical case, the notion of distance. So the code distance determines what is the maximum number of errors which can be detected and what is the maximum number of errors that can be corrected. So if, let's say, if the distance is d, which means if d bit flips happen, then it will be, like, in certain scenario, it will correspond to, like, I mean, you will not be able to, like, detect error, which means, let's say, if d minus 1 bit flip happen, then you will be able to detect it. So the maximum number of errors which can be detected is basically d minus 1. And since for error correction, you set it to the majority value, the maximum number of errors that can be corrected, that is basically d minus 1 by 2. You have to take the ceiling of that. Okay, so we have talked about a few things. We have talked about, the notion of code words, and we are saying that, we are taking basically n equal to 3 bits, and you are using it to encode 1 bit. And then we talk about something called distance, which says that it protects against, like 1 bit flip. But, like, I mean, and if there are 3 bit flips, then you do not even detect it. So like the notion of the distance value is basically 3. So there are 3 quantities that we talked about: n, k, and D. And this will be like, very important moving ahead even in quantum error correction. So N is a number of bits in the code word, A is a number of encoded bits, and D is coded distance. So for N bit repetition code, this basically becomes N11, N1N. And let's say if you are doing a 3-bit repetition code, it's basically 313. Okay, so that's how you know, yeah, like that's what the encoding notation is. Okay, so we have been able to encode the information, but that's not all. We need to our goal should be to perform some computation on the encoded information, and our the way we have encoded it basically 000 and 111, and we need to go from here to here. So let's say so basically what happens that there are different gates that you can talk about through which you can, I mean, basically all these gates will like perform some computation in the encoded space. So one such example is like this logical NOT gate, which will take your all 000, convert to 111, and take 111 and convert to 000. So even in the quantum case, I mean, you do the encoding, and then in the logical space you need to do some operation. So those will be logical operation. Okay. So that's it. That's all the the classical error correction part that we need to know. There are more interesting things like parity check matrices, generator matrices, and like I mean, actually there is a whole there are many nice books on classical error correction that one should consult and look at and so on. But let's say to understand what we are talking in this session, we don't need to like worry about those other things. Okay, so that's the part about the classical error correction. Now, now we will talk about the the quantum part. So we talked about classical 3-bit repetition code. Now like we will talk about quantum 3-bit repetition code. So that's like the genuine. I mean, that's the natural. Like the quantum analog of the classical 3-bit repetition code. So again, it's same as before. I mean, you just put a kit, like yeah, like nothing fancy happening. So the 0 logical is basically 000. 1 logical is 111. Now in quantum mechanics, you can have like you can like the vector, like any arbitrary vector in the vector space can be written as like the superposition of the basis element. So let's say any psi, let's say which is alpha 0 plus beta 1, like it's encoding in the logical space will be psi logical equal to alpha 000. So you replace 10 by 30, like I mean, using this rule here, and 1 by like 31 here. So your alpha 0 plus beta 1 will become alpha 000 plus beta 111. So this span of 0 logical and 1 logical, we are like calling this a code space. So it's basically error-free encoding of a quantum state. It lies in the code space. So you can think that what error correction does is like I mean the sense in which we are talking about is that it takes your information and it encodes into larger Hilbert space, but only a small part of a larger Hilbert space. So like let's say there is some space of the Hilbert space which we will call like code space. And what happened that the errors, they will take you outside, like outside this code space. And your goal is to basically find like where you have come, uh, like where have you come, and then you have to do some operation to get back to the code space. So it's this continuous fight where noise is trying to take you outside the code space, and all the operations that you are doing, it should like basically restore the information like back in the code space. And that's what like all this struggle of quantum error correction is. So let's just, I mean, we talked about error. Let's in the classical case, similar to that. So we talked about like in code words. Now in the classical case, now similar to classical case, we need to talk about the notion of error here. So the errors that you can have here is, for example, a bit flip error. So let's say you have a 0 and there's a x. The bit flip error will transform 0 to 1, and it will transform 1 to 0. Similarly, there can be something called phase flip error, which can like which does nothing to 0 but 1. In case of 1, you pick up a minus sign. Now, if let's say if both X and Z errors can be corrected, like more general errors can be corrected as well. So the goal is to, let's say just focus on X error and Z error, and then, you should be able to put it like against arbitrary. Okay, so so basically, let's say the encoded state, like, I mean, let's look at the encoded state after what happened when it goes to a single bit flip error. So you have, let's say the state is alpha 00 plus beta 11. That's your encoded state. Now, if a single bit flip error occurs, basically single bit flip error can be some action of some operator like identity tensor X tensor identity. So for example, it can take your alpha 00, and since it's acting on the second qubit, it becomes 010, and this beta 11 will become beta 101. So that's how the encoded state looks like, like after a single bit flip error. At this point, we have to be a bit cautious because like the error detection will not proceed same as, like what happens in the classical case. So in the classical case, we discussed that the moment you have for error detection, you just look at whether all the bit strings are, identical or not. But in the quantum case, you should not measure individual qubits in the computational basis, because I mean, like even you will be able to detect the error, but it will also lead to the result in the collapse of the encoded qubit, and you don't want that. I mean, like you want to preserve the information. So instead of that, you should measure symmetries of the state rather than individual bits. So you can measure, for example, the parity of any pair of bits. So you can, let's say, I mean, uh, like let's say if any bit flip occurs, and because of that, like the parity of the like certain pair of bits, that will change. So for example, we call, like these, like, the, let's say if you are measuring two bits, that the if it's this bit string like 00 and 11, they have even parity, like 01 and 10, that has, like we call that an odd parity. So a simple circuit to, like measure parity is here, like which is equivalent to, like measuring Z tensor Z. So you see that, like this Z tensor Z, when you act on 00, you get, like 00. 11, you get 11. So there is no, like it belongs in the +1 subspace of, like a eigenspace of Z tensor Z. On the other hand, like these odd parities like 01 and 10, if you act on, like, Z tensor Z on that, you pick a minus phase. So basically by like performing this kind of circuit, you will be able to, like you can extract some information, and like people sometimes call that kind of information, like syndrome. So that's like, like, I mean, some kind of a prescription that, like, I mean, not a prescription like that, that's more like like some you can call it some kind of a test result. Let's say when you go to a doctor and you're not feeling good, basically these are like, some tests which are performed, and after that, let's say if you get like, minus outcome, it tells you, that something bad has happened. So you can see like there are three kinds of error, like the bit like bit flips error that can happen in the quantum case, like let's say in this 3 qubit case. So these are like X tensor I tensor I tensor X tensor I, and I tensor I tensor I tensor I tensor X. And then similarly, like we can measure the parity of first two bits, like first and last bit, like qubit, and then the second and second and the last qubit. And you see that if the error operator does not commute with the parity operator, you get a -1. On the other hand, if they commute, like for example, this X tensor I and I tensor Z, commute, so you get a +1. So you can basically every time, let's say this error has occurred. So given this error, when you measure these three parities, you will get -1, +1, -1. And you see that, this is unique to I tensor X tensor I. I mean, this will not be always the case, but at least in the case where we're talking. So by looking at, like -1, +1, and -1, you will be able to figure out that, like it's I tensor X tensor I, like, it's a second qubit has gone through a bit flip error. So that's why, like you will detect error. Okay. To correct error, it's very straightforward. You apply the inverse of the error operator, and that corrects the error. So you have, let's say the error is XII. So you just apply the correction operator XII, and this works because, like polys are self-inverse. So there is no problem with, like error correction. After this, like we need to talk about the logical operation on the encoded state. So let's say you have zero logical on that, like when you so basically the idea is that the logical operation that you need to perform in the encoded space, that should mimic their corresponding behavior in the like unencoded space. So like the x bar and z bar should mimic the behavior of x and z, and that's what like we hope, like zero logical should go to one logical should go to zero logical, like in the case of x, and z should like just give a minus sign here. So what are like possible like operators that we can define? You can see that like x is one possible choice of operator which can like act like a logical x operator. Logical z operator can be zi, like because if you have, let's say, something like 0 0 0 alpha 0 0 0 plus beta 1 1 1, like if you act by it on like zi, like it will give a minus sign here. Yeah, so it will act, it will like mimic the behavior of zi, but you can also take I z z, like and any of them work. So I mean, one could ask, what are the like I mean, how to determine the set of possible logical operators and so on. Actually, you can determine all this using something like in the stabilizer formalism, like quite straightforward. Yeah, so maybe we will discuss that. Okay, so we discussed about like so far how to encode information in the quantum case, like what are the code words, what are the errors. Then we talked about like the encoded state after a single bit flip error, error detection, and then error correction. Now yeah, also the logical operator. Now we need to talk about the notion of distance, and to talk about notion of distance, like I mean, we need to understand like something similar to Hamming distance. Here we need to talk about something called weight of an operator. So the weight of an operator is a number of qubits it acts non-trivially on. So for example, if you have xii, its weight is 1. If you have zzz, its weight is 3. So it's non-identity, like operators in your like in your poly string. So let's say if you have xi, its weight is basically 2. And the distance of a code is minimal weight of any non-identity encoded logical operator on the code. So you look at all possible, like logical operators, and then like we basically look at the non-identity logical operator, and among them, the weight of the minimum weight logical operator that gives you, the distance of the code. So minimum weight of the encoded x is basically 3 because it's like x. But in the case of z, you had like I z, sorry, not I z z. You had z I z z z, I z I, or let's say I z. Now in this case, like the minimum weight is like 1, like here. So this is 1. So let's say if the distance is, like here, so the x distance is basically 3, but the z distance is 1. Now, if x distance is 3, that means it can detect 2x errors. But because the z distance is like 1, it can detect like not even a single z error. And like and why should this happen? I mean, this is also like, I mean, easy to see. Happens because I mean. Because the code is, I mean, the code that we constructed is very classical. It was just, like, I mean, simple repetition. And so it was giving us protection as expected against like X error, but it was not giving any protection against the Z error. Okay. So yeah, I mean, you can always, like, I mean, write all this, like, any kind of NK. You can use this NK denotation in the quantum case also. And, like in the classical case, you have this single bracket, like in a quantum case, you just use like something double bracket. So to capture all this, the formalism that people use often, and which is like, I mean, very useful, is this thing called stabilizer formalism. So actually, most error correction codes can be studied via the stabilizer formalism. So it's like Shor code, Steen code, 5-qubit code, CSS code, Tori code, planar surface code. Like, I mean, you can study via this formalism. Even like, I mean, let's say topological codes, like this is the the widely used formalism to study it. And you can use this formalism to like derive encoded logical operators and so on. So the stabilizer code basically is a quantum error correcting code. I mean, like, it's like a circulant definition that can be defined in the stabilizer formalism. And for that, one needs to talk about what is a stabilizer formalism. I mean, which, like, I don't need to go in detail here, but I mean, yeah, like, I mean, you can find it somewhere. Like, I mean, there is like a rich theory of a stabilizer formalism. But for the moment, like, you can see this is how stabilizer codes are defined. But like, I mean, like, to specify a stabilizer code, you need two sets of operator. You need, like, stabilizer generators and encoded logical operators. Actually, like, this will be actually enough. Like, you don't need a encoded logical operator. Actually, from here you can determine the logical operator. Okay, so let's size A be a bunch of like code word basis states. So we say like the set of poly operators which leave all code words like code word basis state size A invariant, we call like that an stabilizer group. So let's say you have a
poly operators.
sorry. Yeah. So basically, like, I mean, it's like a set of poly operators which leave all code word basis states like invariant. So like that's what we call like a stabilizer group. And a stabilizer operator or a stabilizer element is nothing but like but the element of this stabilizer group. So you have a like you have some subspace like where like your let's say a bunch of code but basis states, and basically that subspace is like spanned by your code but basis states, and the elements of the stabilizer group that leaves your like basically actually the entire that code space like invariant. So like, I mean, a simple claim that one can make is that the set of stabilizer operators must commute. And that is very easy to see, like, because let's say if one element is PK, other element is PL. Let's say they don't commute. Let's say that is like, that's not zero. So like Paul is they either commute or they anti-commute, right? I mean, so let's assume that like they anti-commute. So now if you add PKPL on some psi, which is in code, which is a code word basis state, that will be equal to, like, I mean, PL, like PK psi, because PL is an stabilizer, which is equal to psi, but this is also equal to minus PL PK psi, which is equal to, like minus psi. So you get psi equal to minus psi if like if your stabilizer operators don't commute. So they must commute, like, yeah. So like the elements of the stabilizer group, they basically commute with each other. So the any group G, like, you can specify it by a set of generators, like, I mean, so let's say we have this stabilizer group, you can, like, to specify it. I mean, you don't need to talk about every element of the group, but like you just need to talk about the generators, and the generators are enough. And in fact, you can use this very beautiful theorem which says that for an abelian group of, abelian means that, like, I mean, object commute, and like the elements commute, and the stabilizer group is abelian because the elements of the stabilizer group, like they commute. So for an abelian group of self-inverse operators, which happens in our case because we are working with poly operators and polys are self-inverse. So for an abelian group of self-inverse operator, this condition is satisfied. Any element of the group can be written as, like G can be written as Gj alpha J, where Gj is, like it can, sorry, alpha J01. So let's say if the number of generators that you have is M, let's say the total generators that you have M. So using, so like in terms of these generators, you can write any element. So the total possible elements that you will have basically correspond to, like this alpha J's that we can have. So, like, I mean, so it basically you basically convert it to, like counting the number of a strings problem. So the total number of such M bit strings that you have will be basically, like 2 to the power M. So let's say if you have M generators of your stabilizer group, that the size of the group that you have is basically 2 to the power M. Okay, so the size of the group, like, I mean, we have is like, 2 to the power M. Let's K is the number of logical qubits. Let's say N is the number of physical qubit, and let's M be the number of a stabilizer generator. Now you see that every time, like, I mean, since all of these operators commute, and every generator will have eigenvalue, like +1, or -1. So what happens that, like you start with, like some Hilbert space of size 2n, and then like, let's say assume this is your Hilbert space. So, like the first generator will break it, like, divide it in two parts, +1, -1. Let's say the second generator will, like again divide it in two parts, like, sorry, +1 subspace, like, and -1 subspace, like, and the entire thing is +1 subspace. So you see that, like every time you act by a generator, like it cuts the Hilbert space, in a in half. And if you, let's see the total like m generators, basically you go from, like it goes from 2 to the power m, like it gets divided by 2 to the power m. So it's like, with m generators you are able to, like, break it. The size of the subspace where you are encoding the information will be 2 to the power n divided by 2 to the power m. And let's say if there are k logical qubits are encoding here, let's say if the space has k logical qubit, then, like that size will be 2 to the power k. So from here you can see that 2 to the power n by 2 to the power m is 2 k, and then you can take log, and then from there you can get, like m is equal to n minus k, or in other word, like n is equal to m plus k. So you see that, like, I mean, we are talking at a very abstract level in terms of, like, operators and so on, but this is already giving us, like, some indication of, let's say if you have m independent, let's say, generators in your stabilizer group, then the number of logical qubits and the number of physical qubits are there. They are basically related via this relation. So I mean, yeah, I mean, if let's say if m is very large, then in that case, like, k will suffer, and so on. Yeah. So you should have, like, I mean, basically your number of logical qubits will be k equal to n minus m. Yeah, like, this is how it will be. Yeah. So we will be using it here. Okay. So our m, like this we just looked at. So let's look at, like this 3-qubit repetition code. So in the 3-qubit repetition code, the 0 logical was 0, 0, 0, 1 logical was 1, 1, 1. Here the n was 3, k was 1, like, because we are using 3 qubits to encode 1 qubit. So the m that we have is basically 3 minus 1 equal to true. So basically, like we have, like, two independent generator corresponding to the underlying, like, stabilizer group. So the order of the stabilizer group, I mean, we discussed before, will be basically 2 to the power m. So from here, since m is equal to 2, like the order of the stabilizer group corresponding to the 3-qubit repetition code is basically 4. And the stabilizers are nothing but, like ZZI, ZIZ, IZZ, and III. Now this very much remind you, like, I mean, like what we looked at before, like, I mean, like those measurements that we were, like, measuring to, like, find or whether some error has occurred or not. So they were basically some stabilizer measurements that we were performing. And III is, like, I mean, trivial, so, like, we don't care about it, but it's in the stabilizer group. Yeah, I mean, yeah. Okay. So let's look at, like the error detection in the, let's look at the error detection in the stabilizer formalism. So we can detect errors on the stabilizer code by measuring the stabilizer operators. So we had, like, a bunch of stabilizer operators, and actually m measurements like, suffice, because, I mean, if you know the value of all of the stabilizer generators, then that already tells you, like, I mean, where you are in the Hilbert space, and then you can bring the like the uh, uh, like the corrupted state back in the code space. Now you see that we have m equal to n minus k. So m scales linearly with the number of physical qubits. So the number of measurements that you need to perform, that is not very bad actually. Like it scales linearly, and like the object that, like, I mean, that will be relevant for us, like, which will tell us, like, what has happened to our code state, is this object called syndrome, which is the outcome of the measurement of a given stabilizer generator. So basically you will have different stabilizer generators, and you will, like, you will measure them, and that will give you, like, like syndrome, and you have, like all the like, uh, like, vector of syndrome elements, and that will tell you, like, I mean, from there you can infer, like, what error has occurred. Okay. So by the way, like some people are asking chat, like, questions in the chat. I think any of you, if you know the answer or something, I mean, like maybe you could answer them. Like otherwise I could just, like look at it towards the end. I think, yeah. So I think to save some time, we could, like, I mean, other people can try to answer the questions. Yeah. Okay, so let's look at the encoded logical operators in the stabilizer formalism. So for the 3-qubit repetition code, we had like 0 logical was 0, 0, 1, 1 logical was 1, 1, 1. So the psi, which is like alpha 0 plus beta 1, like after encoding it becomes alpha 0, 0 plus beta 1, 1. You know. And the logical operator basically should take like your alpha 0, 0 plus beta 1, 1. Let's say the logical x should take you to like alpha 1, 1 plus beta 0, 0, 0, and like z you can define it. So like I mean we saw that instead of zii we could have also used izi and iiz. So how do we know like I mean like how can we determine like basically this like the set of all logical operators, and this is I mean this is actually like very straightforward in the stabilizer formalism. So let S be the stabilizer group, and let psi be a state in the code space. Let's say we have some code space C, and let's say psi belongs in that code space. Now let L be a logical operator. Now what happened that like let's say you take any Sj from your stabilizer group, Sj psi is psi, like I mean for any Sj in your stabilizer group. Now, what it tells you that if let's say if L is a logical operator, then L times Sj is also a valid logical operator. So like L times Sj psi will be L psi, like for any Sj in psi. Sorry, any Sj in the set of a stabilizer operator. So given a logical operator L, actually there exists a family of 2 to the power m operator LSJ that act equivalently on the code space. And that's why like I mean you could see here that like there were 4 different operators, like I mean, and they are equivalent to each other via multiplication by like some stabilizer element. Yeah. So that gives you like the set of logical operators. Actually, you can characterize it much nicely. So a logical operator, like what do we want from it? We want it to like send an element of the code space to another element in the code space. At the same time, it must commute all the elements of the stabilizer group. Like, I mean, that's what we want. But it should not belong in the stabilizer group. So a logical poly operator must belong to the centralizer of the stabilizer group. Actually, like centralizer of the stabilizer group, but should not be in the stabilizer group. So the centralizer is basically is defined, the centralizer of a group, like of an element Z of a group, is a set of all elements of G which commute with it. Like I mean, yeah. So let's say you have some Z, and let's say you have some group G. The centralizer will be like all those X in the G such that XZ equal to ZX. Now you can you can talk about centralizer of even a a subgroup of a group. So basically, let's say you have a subgroup H and you have the group G. The centralizer of H, like I mean, the centralizer of H in G is basically all those X in G, such that for all H in like H capital H, XH equal to HX. Yeah. So basically, it tells you that I mean what we want is that the logical poly operators, they must commute like with the elements of the stabilizer group. So it means that like it should be in the centralizer of the stabilizer group, but like you do not want your logical operator to be a stabilizer operator, which means it should not be in the stabilizer group. So it should be in the centralizer minus the stabilizer. Yeah. Okay, so that's very nice, because now you can look at like the minimal weight of any operator. I mean, okay, I should modify it, which is in the centralizer but not in the stabilizer of the code, and that will give you like the distance of the code, because this is how you can capture the logical operators, and then yeah, you can look at it. Yeah. Okay, so in the stabilizer formalism, you could see that, like, I mean, the stabilizer group, like for the repetition code is given by like ZZI, ZIZ, IZZ, III. So this was the stabilizer group. The centralizer can be is here. In the NKD notation, it's like 311 code. let's say if you think of, like there's a very nice famous code, which is 513 code, which, which takes 5 logical qubits, protects, like, five physical qubit, protects 1 logical qubit, and has distance 3. Its stabilizers are, like given here. This is nice because now you can, like just talk about stabilizer, like actually the stabilizer generator. And once you know the stabilizer generator, that like tells you the stabilizer group. And after that, you could talk about, sorry, you could talk about, like the logical operators by just looking at, the centralizer of the stabilizer, and like, and from there you could calculate even the distance, and yeah, that's it. And on top of that, there are very nice formula like, n is equal to m plus k and so on that you could use. So by like, just by talking about the generators of the stabilizer group, you can, like specify uh, everything in the stabilizer formalism, like the logical operators, the code space. Code space is basically the subspace of the Hilbert space, which, like stabilized by all the elements of the stabilizer group, which is actually generated by the generators that which you are using to, like, specify. So you just need to talk about, like what are the generators of your stabilizer code. Once you talked about the generators, everything else is fixed, like from there, because then that gives you, the number of generators gives you how many logical qubits you have, and that tells you what are the logical operator, because you look at the centralizer, and then from there, like you can find the distance of the code, and that's it. So that, like concludes basically the stabilizer formalism part. I still have, like, 20-25 odd minutes something. So I will, yeah, so I just plan to cover just the stabilizer formalism, and I was thinking that I will cover Tory code if time permits, but it seems that time is permitting. So I will, like, cover the Tory code also. Yeah. So it's the Tory code is a simplest example of a topological code. And in general, let's say if you, like if you want to understand, like how topological ideas are, let's say, relevant for quantum error correction. Like in the beginning, I mentioned, right, there is a set of lectures, like, which tutorials actually, like, which I gave last year, where, like, all of these topological ideas, and like, homology, cohomology, how, like, that's relevant. Actually, I talk here. So all of this is basically recorded. And today I'm just trying to cover, the first two part, which will be helpful to, like build the follow-up content and so on. Yeah. So yeah, you can like the slides will be posted later, but and then you could, like scan the QR code, and like look at all these videos, like whenever you feel like. Yeah. Okay, so let's just talk about, the Tory code part, and let's see, like, until where we can, like proceed here. So it's a simplest example of a topological code. And yeah, you can see that, like in a Tory code, like there are two kinds of loops, like, which are called, like non-trivial loops. Like these loops, like, cannot be deformed to a point or also to each other. Like, they are inequivalent loops. On the other hand, let's say, sorry, if you have some kind of a loop here, like you can actually deform it to a point. So, like there is presence of some hole here, or let's say, like, there is this hole here, right? In the middle, like these kind of holes, like, lead to actually the right mathematics to capture it is like homology and cohomology. But, like actually we will not need here. Like, we can just, like, this is just for intuition I am mentioning. So the two loops, like, you cannot deform to each other. Like, and these two loops will be like, like later relevant, like when we talk about, the logical operators actually for the Tory code. So in the Tory code, basically you have a L cross L grid, and the qubits, they are basically, like at the edges. So you see that there are, like three kinds of objects which you have. You have like this zero-dimensional object, which are called vertices. You have like this one-dimensional object, which are called edges, and you have, two-dimensional objects, which are called, like these plaquettes. And the qubits, they live on the, like all of these edges. So you can see the total number of edges in a L cross L grid, which has this periodic boundary condition. So let's say if you take a L cross L grid, and let's say you have a periodic boundary condition, like, here you see, right? I mean, it's like it, yeah, like it wraps. So you will see that it becomes a torus. And the total number of qubits that you have, like when you have a L cross L grid, will be the total number of edges, which is, like, I mean, it will be basically, like 2L square. Yeah. So, so yeah, so basically, like we have that the n, which is the total number of physical qubits, that will be 2L square. So we will, like, gradually try to, like build like what is k, what is d in our formalism and all. So the total number of edges is basically L square plus L square is equal to 2L square. Each edge corresponds to a physical qubit. The total number of physical qubit is 2L square. So that gives us, like n. Now, like, I mean, the question is what is k and what is d. So we will see that later. So the total, the stabilizer generators that we have are given in something called terms of, something called plaquette generators and vertex generators. So plaquette generators are defined in terms of plaquette. So, like, I mean, the two-dimensional object. So it's like Z, 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 Z. Like, that's how you define a plaquette generator. A vertex generator is basically corresponding to a vertex. You can, like define like X, 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 X. Yeah. And so there are like, L squared such plaquettes. So the total of like, total number of plaquette generators that you have is basically L squared. And similarly, total number of, like the vertex generators that you have in this way, like will be basically, like again L squared. Now the point is that, we are working in the stabilizer formalism, and we have to ensure that, like our, like, the generators, basically all the stabilizer generators commute. So obviously, like any two plaquette generator will commute, because it's like it has only Z. Any two vertex generator will commute also, because, that's also no problem. Like it has all X. But the question is, like, can plaquette and vertex operators commute? And they will commute, because you see that like any two of such operator, they will either not share any, like there will either be no overlap, or they have, like overlap at even number of places. And we know that, like even though X and Z, like, don't commute, if you have even number of X and even number of Z, it commutes. And that basically, like proves that the plaquette and the vertex operators, they basically commute. Yeah. So an important point here is that, like a pair of plaquette operator, let's say if you have a pair of plaquette operator, they either do not share a boundary or have only one shared boundary. So let's say if you take one plaquette operator, another plaquette operator, like, I mean, yeah, like, eh, I mean, because what will happen that, like if you multiply them together, like at the, like, I mean, whatever is there, let's say something here, what will happen that, because Z times Z is identity, it leads to, like, I mean, it's like an amoeba, right? I mean, it expands. Yeah. So when you multiply like plaquette operator, the resulting operator will include Z operators that act on the boundary of the combined plaquette operator. So you have, let's say, like, like, I mean, just take something like this. You have something like this, and then another operator. Now, what happened that at here, like, everything basically multiplies and becomes identity. So what you are left with, is just this. Yeah. Okay, so now you can see that, like, I mean, let's say I multiply all my plaquette generators. So if I multiply all my plaquette generators, it will, like, I mean, it will cover the entire lattice, and like, I mean, and because it's periodic, like, I mean, I will have nothing left, because, like, there is no boundary. So I mean, basically it becomes identity. So the product of all like plaquette generators, if you multiply all of them, it's basically identity everywhere. And that's a constraint. So we started with L square plaquette, like, generators. And then because of this constraint, the total number of plaquette generators, like, I mean, the independent plaquette generator that we will have is basically L square minus 1. Okay. So we talked about, like, I mean, we talked about all these placate generators and vertex generator, and then we said the number of independent placate generator is basically L square minus one. You can, like you can do the similar calculation for the X operators by looking at our vertex generator by looking at something called a dual lattice. So given any lattice, you can, like you can define, like a dual lattice. So for example, like to construct a dual lattice, you have to interchange placates with vertices and you have to reorient edges accordingly. Okay, so basically, like you see that here also, like there is this this dark like in line, but there this like this dotted line, and this dotted line, this the lattice due to a dotted line, that's basically, like that's the dashed lines basically indicate the dual lattice. And qubits are where, like your dual lattice intersects, like the primal lattice. Okay. So but I mean, we are working with the kind of lattice which is self-dual, like I mean, which means that, we are working with a square lattice, right? And for a square lattice, the dual lattice is also square. If you, on the other hand, if you had to work with some more complicated lattice like hexagonal lattice, its dual lattice will be, like a triangular lattice. So these bracket operators, they become a vertex operator in the dual lattice and vice versa. And the dual, like I mean, and the vertex operator will become a placate operator. And, like I mean, but I mean, our case, the things are very nice. We are working with, like the self dual lattice. So you can play the same game, like for the vertex generators, and you will cover the, like multiply them, and you will, like, it will be everywhere identity. So the number of independent vertex generators, that's also L square minus one. So you see that the number of independent vertex generator is L square minus one. Number of independent like placate generator is also L square minus one. So the total number of independent generators that you have is 2L square minus two. So your M is actually 2L square minus 2. So, and we had n equal to 2L square. So then we can use n equal to, uh, n is equal to m plus k. So k is n minus m. So k is basically 2 in our case. So you can see that, we were looking for k, and for a like Tori code, the total number of the logical qubits that you can have is basically, like two logical qubit. So the number of encoded qubit is 2. I mean, we just, like we just see like how it's possible. Yeah. So that's 2. So that fixes 2. Now the question is, like what is d? Like, I mean, what is a, like a distance for the Tori code? So to talk about distance, actually, like, I mean, if you remember, we said that, like the encoded logical operator, basically it's the distance of, it's the weight of the smallest weight non-identity logical operator. Like that's what the distance of a code means in the stabilizer formalism. And basically we will have a bunch, like we should have we have like, two logical qubits, which means, like we will have two Z operators like Z1 and Z2 and X1 and X2. And we have to look at, like, I mean, all possible representation of Z1, Z2, X1, X2. We have to look at the weight of the minimum weight encoded logical operator, and that will give you, like the distance of the code. So what are the requirements for the encoded logical operator? They must commute with all elements of the stabilizer group. They must not be an element of the stabilizer group, and they must satisfy the commutation and anti-commutation relation of the poly operators they encode. Yeah. So these are the conditions, like if you recall, like we had. So let's say if you have, like let's see how does the encoded Z operator will look like. Now your encoded Z operator basically, yeah, like like the encoded Z operator should not be any loop, right? I mean here, because any loop you can write it as product of, like your placate generators, and you will be able to form it. So basically, like, it will be in the stabilizer group, which means, and then like, then one can say, okay, it must be a string, like it can be sort of a string. Yes, a string makes sense. But let's say if you take a string, any string that you have, it will basically commute with your Z operators, like the placate operators, but it will not commute with, like the vertex operators, which are at it at the end, because at the end you will have a single Z in together with basically single Z at the place of intersecting with single X, and the single Z and single X do not commute. So basically any string that you have uh, at the boundary of the string, basically your X operators will not commute with that string Z operator. So that is bad, so how can we salvage it? So the only solution is to find a string of operators which have no end. Like it should be a loop, but it cannot be a trivial loop. So what it should be? So it should be a non-trivial loop. And that, that tells you, right, that there are, two non-trivial loops that we had, in the Torahs, and using that, then we can define, our Z operators, and analogously, we can define the X operator. So your Z operator, you can define something like this. Let's say the first Z operator, and the second Z operator you can define like this. So so these are like Z logical operator. Logical X operator has to, on the first qubit has to anti-commit with your Z, so it should like intersect it one time. You can take it like this also. Whatever. Only thing matters that it should correspond to a non-trivial loop. And similarly, the logical X operator on the second qubit, it's like this. Yeah. So this is how you construct your logical Z and logical X. Actually, like if you look at from homology perspective, you can look at something called the first homology group, and that will tell you how does the logical operator look at. And by looking at the size of the first homology group, you can study many of this interesting behavior. Yeah. So you see that you have this is a logical operator. Actually, this is also a logical operator. Because anyway, it's just this non-trivial. Like this is also a logical operator, because you can multiply with a stabilizer, and it will still remain a logical operator. So this is nice. It can tell you that how does the set of logical operators look like, and distance is nothing but the size of the minimum weight logical operator. So you can see that that will be the weight of the minimum weight logical operator, and the minimum weight logical operator should be correspond to the shortest non-trivial loop on your on the torus, and the shortest non-trivial loop has size L, so the distance is basically L. Yeah. So that that answers this construction. So our N is 2L squared, K is 2, and D is L. So this is nice. So we got the code distance also. So this is the the NKD notation for the 2D code. Okay. So how do we do error correction via the 2D code? So we can look at it. So there is this error detection. Error detection as before. We can detect errors on the stabilizer code by measuring the stabilizer generator, if you remember from before. And the syndrome was basically outcome of the measurement of a given stabilizer generator. So whenever an error E happens, the stabilizer generator that don't commute with E will output -1, like we saw earlier, like in the case of a quantum repetition code. That's how one can find whether some error has occurred or not. So let's say you have a Z error on a single qubit. Now, which stabilizer generators anti-commute with it? So though you see that a Z error on a single qubit will anti-commute with the vertex operators which are immediately adjacent to it, because the overlap is just a single qubit overlap there, and they will anti-commute, and that will give you minus sign. So that will tell you that that qubit has gone through a Z error. Now let's say instead of a one qubit, you have two qubit, it's a string of error. Then again you just look at the operators at the boundary, and that tells what error has occurred. In fact you can have some error which can which can be like a string, like Z Z Z Z Z, and then you can just find you can detect it via those vertex generators which are at the boundary of the string. Yeah. So let's say anytime you start measuring, you will get some of the vertex generators flipping, their sign will become like -1, and then the error should be basically a path from one vertex generator to another vertex generator. Yeah. Okay. So basically, given any string on the primer lattice, the only stabilizer generators have their outcome -1 or the vertices at the two end of the string. That is what we just mentioned. So what about the X error? Like, this was all about the Z error. What about the X error? So you can do the similar analysis, like for the on the dual lattice for the X error. So that was, like that's how you can, detect error. So like, let's say once you have detected the error, the next task is, like, to correct the error. Yeah. Okay. So main task in the error correction is the identification of the error operator to apply given the syndrome. So for example, in the case of poly, just apply the inverse of the error operator. But what happened that for the and yeah, like for the self-inverse poly operator, you can just apply the same operator. But you can do even, like even more interesting things. So for example, let's say, the original error was like this. And as long as, let's say, the operator that you apply, let's say, so you apply this operator, what will happen? So let's say the original error was this, and you end up applying something like this. So as long as, like the original error plus the recovery operator that you applied, like, if together they form a stabilizer, you are okay. The reason being, let's say if you started with, some initial psi, if some e occurred, and after that, you apply some e prime. If e prime times e is some s, then s psi will be, like psi, where psi is in a code space. So as long as, like when you apply an e prime, such that e prime, like e is equal to some stabilizer, you are fine. Yeah. So that gives us, like some room. Yeah. Okay. So that's how, like you do the error correction. I mean, there are details to it, like, I mean, there are the decoding and so on and all that I will not be able to cover today. But that's it. I think we are towards the end. So now the final thing that I would just like to mention, that, like there's the rich connection of all these objects with, like condensed matter physics, and you should actually look at, like this very nice textbook, actually chapter 17.8. Yeah, like the spin liquids and so on. So the Tory code Hamiltonian, actually Tory code can be, like can be used to, like can be studied by some Hamiltonian called Tory code Hamiltonian, where, like you take all vertex operators and you make this AS operator, and then the, placate, and then you get this BP, and you sum them, and this Tory code Hamiltonian. And this Hamiltonian, the ground state has degeneracy 4, which makes sense because, like, which is analogous to, like having four-dimensional space where, like the two qubits live. And yeah, like all your AS prime commute, BP prime commute, AS BP commute, as we saw before. So that concludes actually, like, all that I wanted to cover. And yeah, I mean, yeah, I think Andrew can take the charge from here. Maybe I will, then just stop the recording.
All right. Yeah, thanks, Kishore, for the nice introduction to error correction. So I guess we can open the floor for